Yes, thank you very much, Paul, for this kind of introduction. And thanks for the invitation to this autumn lecture. So I'm with Fraunhofer Heinrich Hertz Institute, which is one out of more than 60 institutes of the Fraunhofer Society. And Fraunhofer Society is the biggest public research unit, I guess, worldwide. So the different institutes cover all technology areas, and the main mission is to perform applied research. Our institute is is very much involved in video coding. So all the most recent video coding standards have been invented and developed in our institute, H.264 and H.265, for example. And in our department, we deal with the whole processing chain, from capturing scenes with multiple cameras, processing multi-view video, and also render this type of data to provide new media services. So today I will talk about virtual reality, the pathway forward. And after some general aspects, I will discuss the current challenges of 360 video. I will then go in detail on some coding and distribution aspects. Then I will present some recent technologies and interaction in virtual reality. And finally, I will conclude with volumetric video, which is a new cutting-edge technology which receives quite a lot of interest. So, first of all, virtual reality is not new. There have been several approaches since last century, and even 360-degree video is not new. So there were already some presentations at the Industrial Fair in Paris. And there are several niche market applications for virtual reality, flight simulators, interactive cave environments, and so on. But these type of applications required bulky hardware setup and quite complex visualization systems. So, but we have a new VR hype now. So some quite well-known people are using these kind of new devices, and I guess as every one of you has a mobile phone, a smartphone in his pocket, you are the target group for virtual reality, because you can use your smartphone to experience at least 360 VR video. So there is a focus on innovative VR headsets, and there are some well-known devices shown here. So there is a suitable and affordable technology available now, and therefore VR becomes quite prominent, quite interesting. There is a huge market, and as said, each smartphone might be a high-performance VR device. So there are promising market forecasts for virtual reality. There are high investments in the VR market, and 2016 is considered as year zero for market penetration, and 2020 might act as the ramp-up point for worldwide investments. But the market forecasts depend on the client platform, which will be mobile devices, console applications, or PCs. So there are basically two main categories of the new VR market. First, the 360-degree video, virtual reality, and So this is mainly based on smartphone technology. So it's a wireless and mobile application with onboard video playout. And there is the possibility to watch 360-degree video in 2D or 3D. And there is the degrees of freedom, how to experience the virtual world is basically or mainly 3 degrees of freedom. So just look around experience with some applications with limited 6 degrees of freedom, which means a little bit of head motion parallax. On the other hand, there is volumetric video or volumetric VR. This is basically a PC or console application, currently mainly tethered, but there are already untethered devices coming out. And it mainly offers the experience of computer-generated images, requires high-end graphic boards to render the virtual worlds. So it's mainly 3D graphics, but for these kind of devices, there is a full 6 degrees of freedom walk-in navigation possible. So if we talk about the required resolution for final video panorama, we need to have a look at the perception capabilities of the human eye, and the acuity of human eye is about 1 arcmin. So to reach this maximum resolution, 60 pixels are needed per degree. So if we consider a full sphere, 360 in horizontal and 180 degree in vertical direction, we require content of 22K times 11K pixels to represent full 360 video panorama. And this resolution is then completely enough because the human eye cannot resolve more than that. The displayed field of view is about 120 degrees, so we require 8K resolution per eye for a headset display. So this is what is required looking at our visual system. If we compare these figures with the existing camera systems, so the acquisition side, then there are several quite well-known camera types on the market: Nokia Oso, Google Jump, Jones Neo, and so on. And they all have different opening angle and offer different resolution. And if we recalculate the resolution per degree and eye, all of the common camera types are far from fulfilling the requirements to perceive 360 video at the necessary quality. However, there is the OmniCam 360, which is developed by our institute. And at the moment, we use 10 wide-angle cameras, currently at HD resolution. And with this current setup, we reach almost 28 pixel per degree. And the next version of this camera, by using 4K cameras, we are close to the boundary of the human visual system. So if we look at the video cameras again. State of the art is currently 10 to 20 pixels per degree, but we require 60 pixels per degree. So there is a factor of 3 to 6 too low. And if we look at the display side of the headsets, the state of the art is 1 to 2K for 96 to 110 degree, but we require 8K for 120 degree. So there is still a factor of 4 to 8 missing. So the conclusion is that the current state-of-the-art cameras fit well to the current worse state-of-the-art VR headsets, but they are definitely not future-proof. So what are the challenges of 360-degree video? There are two different workflows for 360-degree video, which are called direct stitching by using mirrors, depth-aware stitching, and depth-enabled light field rendering. And you already see on this slide that several different manufacturers offers cameras in the different areas. And I will go in detail on the first approach and the second one, and just touch a little the last approach, because this is the more challenging, or the most challenging one. So what is the reason for using mirrors? Ideally for 360 video, all the focal points of the cameras should coincide at a central position, so then we can stitch all the images together and achieve complete 360-degree video. So the main principle is by using these mirrors is that the virtual image of the focal point is in the center of the mirrors, and if we consider a second camera, also the second focal point, the virtual focal point is at the same position. So this ends up in this ideal configuration. However, if we set up a camera system like this, there is no overlap. So we need at least some pixels of overlap to perform the accurate blending between the different camera views. So therefore, we shift the optical center slightly off-center, which introduces some parallax, but with this kind of approach, we still achieve a parallax-free setting of about 30 centimeters in front of the camera. If you consider other commercial cameras, you are not allowed to walk nearby the camera, because you get these parallax effects and you get these stitching artifacts, and you cannot blend the images correctly together. So the basic approach for the stitching is we get the different views of the end camera system. We need to map this onto the 3D surface. So this can be a cylinder or a semi-sphere. Then we have to do color matching and an alpha blending on the stitching borders. And then we have to crop the final panoramic view, and we end up with the full 360 panorama. The example here is just for the 180-degree case, but the same holds for 360. So here's an example of one of our productions. So this is pretty nice production, because in this case the orchestra was seated in the audience, and by looking around you can watch the visitors and the orchestra at the same time. And you also notice that some of the persons are quite close to the camera and we do not have any stitching artifacts. So with this camera we did a lot of productions in the last 4 years. So perhaps the most exciting one was the FIFA World Cup final in Rio. Not only the German soccer team got a ticket, but also the Omnicam team got a ticket, and we were able to capture the complete final and the final ceremony. And then we did a lot of other productions with in the commercial domain, but also different pop concerts and so on. However, this version of the Omnicam 360 was only is only offering cylindric panorama. So especially for 360 VR video watched on VR headsets, panorama with the closed spheres required. So therefore we extended the camera system towards spherical panoramas. And this is a production in LA. Coding issues. So this was the car where the camera was mounted on. Okay, you will experience this video very much better because I brought some Gear VR with me. You can enjoy these productions during the networking cocktail later on. So I have several productions with me, and you can then take a look and experience what we have produced. So this was so far just a 2D acquisition, but with a similar approach using mirror systems, we can also extend this camera system towards stereo. So this requires some special arrangement of the left and right camera. So in this prototype version of the Omnicam 360 3D, we used then I guess 22 cameras, 11 for the left view and 11 for the right view. And for sure the stitching process, this is a little bit more complicated. So we need to compose the different stereo panorama segments for the left and right view. But this is possible, and we also did an example production together with Sony. On top you can see the left panorama, and on bottom the right panorama. So, and here in this part you can notice that the actor is walking quite close to the camera without any stitching artifacts. So what are the pros and cons of such a mirror-based system? I guess our camera is the only one which is offered commercially. So this offers a parallax-free setup, and we can easily stitch the different views, and due to this we achieve high resolution at high frame rate. There is just a very small overlap of 20 columns where we perform the stitching and blending. And for the stereo case, we are able to adjust the stereo baseline, so we can adjust the depth impression. For both type of systems, we have real-time processing chain for 2D and 3D, and therefore this camera is capable for live transmission. Spherical extension to the full 360 sphere is difficult, but for half sphere it's possible. And on the other hand, another aspect is the form factor, but the current camera weighs just 9 kilo, and you can see on the image on the right-hand side, it's easy to transport. Due to the mirrors, it's for sure sensitive to damages, and it's a cost-intensive solution. However, compared to the Nokia Oso, for example, we offer this camera in the same price range, but with the given advantages for parallax-free setup. Interesting thing is the camera is calibrated once when we mount the cameras, and after that you can just transport the camera somewhere to the West Coast in LA or wherever, and then start recording. Perhaps there is some fine adjustment necessary, but this can be done by software. So there is no hardware calibration necessary. So coming now to the second approach, the depth-aware stitching, which is the approach basically used by all these other commercial cameras. As said, the main idea is that all focal points are at the same center to avoid parallax. But these commercial cameras like Nokia Oso and so on, they all arrange their cameras in a star-like approach. So therefore, all the focal points are at a circle. So we notice a distance b, which offers the parallax between the neighbored views. So therefore, due to this parallax errors, we need to do, or the manufacturers have to do some sophisticated processing. Here are some examples for stitching artifacts. So you see quite close to the camera, these neighbored images do not fit very well together. And even in the case of motion, some parts get lost, such as the leg of the man. So the approach to achieve a good stitching result is to optimize a stitching plane by registration. So the basic concept is to search for corresponding feature points in overlapping areas, and then to analyze the 3D stitching surface. And you can, with this approach, you can only reduce stitching artifacts, but there is no guarantee to avoid them completely, even in the case if there is a moving scene with people walking around or cars passing the camera and so on. So by doing all this analysis, you can then perform correct stitching, even in the case of parallax between neighbored views. So on the left-hand side, you see the schematical diagram. On the right-hand side, you see some prominent commercial products, NextVR, Samsung Beyond, and so on, which are designed by this approach. So these cameras offer panoramic stereo. So therefore, we call this setup also segmented stereo. A second camera setup is used by Nokia Oso and Joint Neo, and also another version of our omnidirectional camera, which we call Omni Star 3D. And this cameras are using plenty of cameras arranged in a star-like approach, and the neighbored cameras are split in stereo subpairs, so the 3D information, or the left and right view, can be gathered by this splitting. So this is an example of Omni Star 3D. So we also showed this, but in this case, it's not real-time capable. It needs some post-processing and post-production to achieve a good panoramic stereo. So some pros and cons for depth-aware stitching. Small form factor, robust and compact systems, easy handling, no calibration. There are stitching software tools available, and there is an established post-production process available. However, real-time processing is not possible, so therefore the use for live events is quite limited. Usually closed systems, no lens control, and so forth, and so on. On the right-hand side, you see some examples of these post-production tools which perform the stitching for these kind of cameras. The last approach is depth-enabled light field rendering. I just won't go into detail, but again, a list of pros and cons for this kind of approach. I will leave it as is, so you may read this or inspect this slide afterwards. So, if we look into the processing chain, so there is, if we consider some kind of panoramic acquisition system on the left-hand side, there is some encoding and content delivery required to serve different kinds of target devices. The most prominent is the VR headsets, but also tablet applications or UHD TV applications are possible for such kind of content. So imagine large UHD TV screen. You can navigate in your living room in the 360-degree video, but just by using the remote. You can zoom in and so on. The transmission problem of 360 video VR is as follows. We have a high amount of data, even if we look at the necessary resolution up to the limit of the human visual system. There is low latency required for interaction. However, the viewport, so the viewing range you are looking at, is much smaller. And the question is where to crop the viewpoint. So there is one format which is quite common now, especially for mobile devices. This is the equirectangular format. This is usually a 4K video stream, and this can be, with this kind of transmission, you transmit the whole 360 panorama at 4K resolution. and the user then selects on the receiving side the desired viewport. However, if you remember the figures at the beginning, we are far from the required resolution for the human visual system. We did a first live transmission together with Berlin Philharmonic's orchestra. So we offered a real-time stream for the digital concert hall, which is a service by the Berlin Philharmonic Orchestra in Berlin. So we captured 360 video, we performed real-time stitching and transmitted then an UHD and HD stream to the cloud, and the registered users at the digital concert hall were able to stream this kind of content in real time. Another approach to approach the much higher resolution is using satellite transmission. So in this case, we also performed some prototype tests for the native format of the OmniCam 360, which is 10K times 2K for the cylindrical format. And by using a satellite link, we were able to transmit the full 360-degree video at this high resolution. And again, at the receiver side, the receiver can decide about the viewport. At IBC, we presented this case. So in Luxembourg, we installed the camera in different places, and the live 10K times 2K stream was transmitted to satellite, and we received this stream in real time on our booth and presented this video content. And we were able to watch the content on VR glasses or on a UHD monitor by navigating with the remote. Another approach to solve this problem of high data rate is tile-based streaming. So in this case, the 360 panorama is stitched, and then different tiles are created and encoded in a tile bit stream. And on the receiver side, you can then just perform stitching on bitstream level. So therefore, this we can use the high coding efficiency, and we can adapt to the client format. There are different mapping formats for 360 video. I talked about equirectangular. There is also cubic format and cylindrical format under discussion. So another interesting question is how to adapt to the field of view of the client for cubic format. And one approach is to offer the content in different resolutions. And depending on the viewport, the content is updated with a high resolution or higher resolution data. So there is no impact on content preparation at server side. So this is a system overview for tile-based streaming. We have an HTTP server on the left-hand side, which provides the video content in different tiles, in original resolution and low resolution. And then in the user device, the HEVC decoding is performed, and the orientation feedback is performed to select the desired tiles out of the bitstream. So this is an example showing the different viewports and the different high and low resolution content. There is quite a lot of activity in MPEG, and the roadmap is presented here. So by end of 2017, there is the phase 1A, which is all about 3 degrees of freedom, 360 video. The concept is tiling by HEVC, and for audio, an extended MPEG-H is considered. The phase 1B is concerned with limited 6 degrees of freedom, which basically means head motion parallax. So you can perceive a little bit of parallax if you move your head to the left and right. And by end of 2021, 22, MPEG wants to achieve some standards for unlimited 6 degrees of freedom, 360 video, and so on. But there is still a lot to do to achieve this by 21. So now a brief introduction to interaction in VR. There are a lot of currently popular VR input devices available. So if you experience VR application, you want to see yourself, you want to touch objects, you want to move the scene, and so on. So therefore, the interaction with the content is required and necessary. And there are different devices available. For these head-mounted displays are the technical features of HTC Vive are listed. So it's still tethered solution, but there is a mobile approach announced. As you can see, the display is an OLED display, and we have currently 1080 times 1200 per eye, and the field of view is 110 degrees. And thanks to tracking by photodiodes, you can navigate in a tracking area of 4 meter times 4 meter, and walk around and experience the VR as you like. Another example is Oculus Rift. Also tethered solution, same resolution of the display, and so on. A little bit different tracking system, and a little bit smaller tracking area. If you use just one controller, you can extend the tracking area if you use some more controllers. For non-intrusive camera-based hand and body tracking, there are also different devices on the market already. Leap Motion is the most famous one. So you can, the hands are registered or recognized by a stereo camera system, and you can use this information. You get a skeleton of the hands immediately, and you can use this information for animating artificial hands in your virtual scene, and you can interact with objects. We are also working on camera-based tracking. So here you see an application based on the Leap Motion. So the hand shape is recognized, and you can and your own hand is visualized in VR. Body tracking is another interesting approach in order to navigate in the scene if you do not have any sophisticated tracking hardware. So just by using leg motion, we can interact with the scene and walk in the scene. So by rotating the shoulder, you turn left and right, and by putting the leg forward and backward, you start walking. This is used, achieved by using Kinect sensor. And there are other wearable devices, hand controllers, data gloves, and full body suits to track the motion of the user and to transfer this motion and signals for interaction into VR. Now let's come to the last point, volumetric video, which is quite promising and quite an interesting approach. So the main idea is to capture moving persons with many cameras or 3D sensors. And based on this multi-view video setup, the idea is to create dynamic 3D models. So instead of animating artificial avatars, artificial characters with motion capture information, we capture the person as the person is moving, how the person is acting. And the result of this approach is either a wireframe per frame or a 3D point cloud per frame. So this brings me to the required data. Imagine 300 megabytes per wireframe per frame. There's a huge amount of data to be transmitted for some interactive applications. There are several companies and labs working on this topic, not very much, but a few. Some smaller ones like Microsoft, some larger ones like 8i. 40 Views in France is also looking into this, and we are working on this, and we call our approach 3D human body reconstruction.
Calibrated green screen stage. We subtract the background to compute silhouettes.
So this is the Microsoft approach.
The first step generates a 3D point cloud, starting with stereo depth maps from RGB and IR pairs. Points from these depth maps are merged and refined locally. Then the cloud is refined globally using a multi-view stereo algorithm. This result has over 2.7 million points with normals per frame. We're viewing tens of thousands of points in this scene. The next stage creates a watertight mesh per frame. We modify screen Poisson surface reconstruction to produce meshes constrained by the silhouettes. These meshes typically have topological artifacts and spurious components. To clean them up, we apply topological denoising and island removal.
Okay, I stop here because I do not want to advertise Microsoft's approach because they are our strongest competitor. But the interesting figure here is they use currently 108 cameras for 360 setup, 55 RGB cameras, and 54 cameras with IR filter for depth from structured light. And they target the HoloLens, so that's their target device. So therefore they have to downscale the 3D models to very poor resolution to be able to render these kind of models in the HoloLens. But you can see the output of the 3D point cloud is 70 million 3D points, so there is a lot of mesh reduction necessary and mesh cleaning necessary to end up with, for example, 10K faces and a 1K texture atlas. Another approach is 8i. They use 40 cameras, also HD cameras. It's also a non-real-time approach, and their output is 3D point cloud. They do not offer a mesh. And you also get an impression about the quality. Another system is provided by 40 Views. They offer different type of complexity for the capture system, 28 to 80 cameras. And finally, organic motion, which they use 14 HD cameras, USB cameras, resulting in this kind of quality. So we also set up acquisition system for volumetric video, and we did some productions in March this year. It was based on a green screen studio setup with 12 cameras. Remember, only 12 cameras compared to 108 by the Microsoft system. For sure, this system is not capturing 360, but I come to this point later. So this was our first setup, and the workflow for volumetric capturing is we receive all the different views, we perform keying to process only the object, then we do multi-view 3D reconstruction, which results in a point cloud, and then we have to do the meshing and the mesh reduction to achieve a format which is capable to be rendered in a rendering engine. So we did some productions so far and presented them at fairs and so on, and this is a short clip on the first production together with UFA, Gateway to Infinity. And a second example is Tiger Tail, which was produced with Trotskind. So a very short story. I hope you noticed the difference in terms of quality. The resolution of these meshes was 80K faces compared to 10K or 20K by Microsoft and so on. So the next step is AR. So this kind of content can not only be used for virtual reality, but also for augmented reality. And here we demonstrate on a standard device, a smartphone or tablet, how to use this content for augmented reality. As said, the first shooting in March was limited in terms of the field of view. So now we are setting up a new studio concept for full 360-degree capturing, but in this case we only use 32 cameras. 16 stereo pairs, again compared to Microsoft, 108 cameras, much smaller setup in terms of number of cameras, but the reason for our quality is the resolution of the sensors. We use 20 megapixel cameras compared to the HD cameras which are used by Microsoft. With this kind of studio concept, we integrate lighting and background at the same time. So we key against white. And with this setup, we are able to generate high quality and high detailed volumetric models. And this is the state, well, almost 2 weeks ago. So you can see the center of the cylinder. You see all the light panels which are mounted, 120 in total. And we will perhaps today putting diffuse tissue in front to have homogeneous white background. Then we cut holes and in the tissue and for the cameras which are mounted and distributed equally in the whole cylinder. We also will have cameras on top. So we expect very high quality footage from this new setup, and we will do our first productions mid of October together with UFA. And yeah, and we expect many more productions in the near future, especially starting in 2018. Yeah, this was not only my work, but work from many, many colleagues in our department. So thanks to all of them, and thank you for your attention.
Thank you. Do we have any questions, please? At the back there.
I realise, and I think your work's marvellous. I think your work's marvellous. Is that better? And I realise it's still in its infancy, but is there not a danger that we could end up with a sort of gigantic VHS beta thing here, where everyone's got their own content and none of it can operate between different viewing type devices? I think that is already kind of ringing alarm bells for me.
Well, this technology offers dynamic 3D models, so it's the result is representation of movement of human being, of an actor, which is quite natural and realistic. So you can do a lot of things with this. So it's up to the application how to use it, and there are many interesting applications where this kind of content is desired. I don't know if this answers your question.
No, it's just I know I'll be the guy with the Betamax player. Thank you. Questions?
Hello, Peter Barnett, independent consultant. Do you see any editorial constraints brought about by this? I'm thinking in terms of zooming to produce dramatic effect and also that sort of thing. And secondly, the scenes that you have, the pictures you've showed of studios and so on are terrifically complex. Do you see this migrating successfully into the real world, to studio sets, to the street and so on, to remove constraints over the type of material that broadcasters perhaps and others might want to produce?
Well, you mean zooming into the to the 3D object, the dynamic 3D object. This is a matter of quality and resolution of the object, and I guess with our approach you can really go very close to this reconstructed models. Concerning the setup, I agree this setup which I presented in the very last slide is quite complex, but I mean, we are working on cutting edge. We want to achieve the best quality, the best resolution, the best texture and so on as we are researching on it. But the algorithms we are using, they can also work with much smaller setups. We demonstrated already that we can just use these kind of cameras in a green screen studio, which is available. So we just put the cameras, we set up the lighting, and we can apply our algorithms also on this kind of setup. So I know there are requests, especially from production companies, to have also some lightweight approaches for volumetric video. But I guess overall, if you consider a serious equipment, professional studio equipment, it also costs millions of euros. So from this point of view, if some production company is interested in very high quality footage for new immersive media content, they are willing to invest. And for sure, not every studio will have such kind of setup. I guess in Europe there will be perhaps 4 to 5 studios by end of next year, and then these studios will offer production services for media production companies. So it's not necessary for every a production house to set up such kind of studio. They can just go there and, for example, come to us and perform the production with us. And the costs for such kind of production are much less than setting up this whole studio.
Oliver, I'm aware of the time, so I'd like to say thank you. There'll be opportunity in the cocktail to pick up. I'd just like to say thank you to